Every millisecond, millions of data packets traverse the digital infrastructure of modern enterprises, carrying everything from financial transactions to personal health records. To process that volume, most web applications rely on a standard N-tier architecture. Information enters through a user interface, is processed by application logic, and is permanently stored in a database. Every time data moves from one of these tiers to the next, it crosses a trust boundary. The system must assume the data handed off from the previous tier is safe to process. Attackers focus their efforts on these handover points, testing how the system interprets data as it moves between isolated environments. An attacker usually isn't trying to break a physical server. They craft specific inputs, like directory traversal commands or malicious scripts, to see if the system will execute them when they cross a boundary. Securing modern software relies on the strict, continuous maintenance of state integrity across every internal boundary. Relying solely on external tools, like a web application firewall, to catch bad input after a system is deployed is a fragile strategy. If the firewall fails or an attacker bypasses it, the application is defenseless. True resilience demands that defensive mechanisms be structurally embedded directly into the application's source code. We will look at how software engineers actually build these defenses, exploring programmatic controls ranging from parameterization to database-level transaction rollbacks. The ability to anticipate, isolate, and neutralize unexpected inputs at the architectural level is the exact difference between a resilient system and a compromised one. Let's start at the presentation layer and look at the anatomy of cross-site scripting, or XSS. This vulnerability occurs when an application takes user-supplied data and includes it in a web page without proper validation or escaping, failing to separate the text from the executable context. The user's browser blindly trusts the input. It reads a string of text containing a script tag and executes it right there on the screen, assuming it is part of the application itself. That same failure of separation causes even more damage deeper in the architecture, at the boundary between the application and the database. If an attacker can inject their own SQL logic into an input field, they can manipulate the backend database to bypass authorization checks entirely or extract sensitive records. To prevent this, developers use structures like this Ruby code snippet. Known as parameterization, it forces the database to pre-compile the SQL command entirely independent of user input. The command is locked in place, leaving empty slots for variables. Because the code is already compiled, when the user data is finally inserted, the system treats it strictly as a literal value. Even if the user types a malicious database command, the system only reads it as a meaningless string of text. Parameterization neutralizes SQL injection by mathematically enforcing the boundary between code and data, making execution of the payload impossible. Moving deeper into the architecture, malicious input is only one threat to state integrity. A database's internal ledger is equally vulnerable to logical contradictions, missing records, or unexpected crashes right in the middle of a process. Engineers manage multi-step failures using transaction blocks. Wrapping commands between begin and commit enforces atomicity. Here, it processes the initial command, adding $250 to an account. However, if it finds the second target account does not exist, it hits a logical failure. The database's architectural response to this contradiction is immediate and automated. Rather than leaving the first update in place and creating money out of nowhere, the database completely rolls back the transaction, reversing that initial $250 addition. Permitting a partial update in a multi-step process introduces irreconcilable errors into the data, destroying the reliability of the ledger. Transaction atomicity preserves state integrity by treating complex operations as a single, indivisible unit. The entire sequence must succeed, or the entire sequence must fail. Writing prepared statements in transaction blocks means nothing if those controls aren't systematically verified before they reach a production environment. This verification happens within the software development lifecycle. Teams use two methodologies, static and dynamic testing. Static testing takes place during construction, analyzing raw source code for vulnerabilities before compilation. Dynamic testing occurs at cutover, evaluating the active application with real-world inputs. Even with initial testing, modifying an application creates risk. Applying a patch or feature update can unwittingly introduce flaws not present in prior versions. To solve this, developers rely on regression testing. Regression testing works by continuously reevaluating a large suite of baseline scenarios every single time the software changes, verifying that the new code hasn't broken the old functionality. This automated verification is an absolute requirement for continuous integration pipelines, where code deployments might happen daily. Integrating rigorous testing directly into the development lifecycle elevates software security from an ad hoc task into a mathematically managed engineering practice. Despite parameterization, atomicity, and rigorous testing, the ultimate architectural reality remains: software will eventually encounter an irrecoverable error. The blue screen of death serves as an operating system's ultimate architectural safeguard against a fundamental logic violation. In this instance, the operating system detected a memory page fault occurring in a protected, non-paged area of memory. The system determines that continuing to operate in this compromised state could corrupt the hardware or permanently damage the data. Shutting down the machine is a protective feature. In information security, this engineered response is known as entering a fail-secure state. The alternative is a fail-open state. If a firewall suffers a failure and defaults to failing open, it allows all traffic to pass uninspected. A fail-secure architecture intentionally sacrifices availability, dropping all traffic and locking out users to guarantee data integrity. Professional software engineering does not assume a perfect environment. It operates on the certainty of bad inputs, component failures, and hostile conditions. Secure software development establishes an architectural guarantee that a system's state integrity will be preserved, even if preserving that integrity means forcing the system to die.